Guys hear me? Do you hear me, Melissa?
That sounds great.
All right, we are on.
The lighting is looking a little bit.
Good morning, everyone. Do we have some viewers on the live stream? 58. 58 in Zoom.
There's more in Zoom, so I'll just.
Okay. Uh,
64.
okay, we'll give some people time to show up because we do our midterm makeup bonus points this morning. The midterm average was low, as I'm sure you all know already. It was 57, which is, gosh, lots lower than we hoped, and we feel bad too. I know you guys are reeling a little bit. For those of you that haven't had a lot of college exams, sometimes this happens. You get you get hammered. So don't stress out too much. When this happens, we try to grade the class on a straight scale, of course, but and that's so there's no competition. But if only two or three people can get an A on the straight scale, we have to change it. So uh, be aware that we're if we have to bring the A's down, then everybody benefits. So it's still not technically curved, but there probably will be a shift. Keep it linear, but shift it. And the other thing is, you know, uh, we give exams. It's an assessment. We want to see what you're doing. You have to show us in order to get a grade that you know what's going on. But there's another aspect to exams, and that is we want to know what you know. That is how are you getting it or not? And the first two exams were probably a little too easy, and we were. But this one, that doesn't mean this one was too hard. I think this one was a little too hard. But what the teaching staff needs to know is where are you? What can we expect of you? Are we being effective? Are you getting the things we're trying to get across to you? Because we need to evaluate how we're doing as well. And when you guys do poorly on a test, that reflects that maybe we're not doing our job as effectively as we can. But we want to know where you are so we can address that. Do you need help here? Should we be doing something differently? We'll get lots of feedback from you. And this has been a challenging course. It goes very fast. The technology has been challenging. Everybody's life is challenging right now. We're taking all that into account. We talk about how to make the technology better every day. We worry about the resources you have. Can you get to them? They're all online. Is Prism the best way to get them to you? So we are continuously trying to make it better, and we're going to take these two things into account: the fact that this was a hard midterm and that you didn't do well when we write the final. So we'll try to write the final at a level where we now know you can perform. That is, we don't want to test to your level. We want to challenge you, but we know the range of things that make a fair exam under these circumstances. So we can make those adjustments. I've been doing this for a long time, and I can usually predict pretty closely what the average is going to be after we write an exam. And I was a little off. I was guessing low 60s because I knew it was tough, but it was a little lower than that at 57. So, but we're going to make adjustments. Everybody will make adjustments to keep us on track. Let's see, the assessment exams need to be, there's one other thing I was going to say. There's the test question. Yeah, we'll definitely talk about that. So a couple things. There's one question that we ended up tossing out. So everybody's grade will go up a little bit because of that. It was a question where we asked you, there was a bunch of bond enthalpies in the table, and we asked, could you calculate what was missing? What was preventing you from calculating the enthalpy of formation of ethanol from the information in the table? And you actually asked about the enthalpy of combustion. We said, can you calculate the enthalpy of combustion from the information in the table? And the bond energies, you could not do that because the CO double bond wasn't listed. But you could have calculated it because you did calculate it in another place. And a lot of you said, well, bond enthalpies aren't as accurate as reaction standard enthalpies. That wasn't the point I was getting at, but I can understand why you may have said that. So taking everything into account, we just said, well, that just wasn't fair. And it was reflected that I think only 13% of the people got the right answer, which means no one got the right answer. Because in general, when you have an exam like that, there's about 8 to 10% for every answer. It does spread out. So it was a bad question. And you can tell when we look at the statistics, we can tell it was bad. So we tossed it out. So that, I think that's it. Maybe the other thing that I was going to say will come to me as we go. We're going to move on. It might be a good time to talk about this guy. So I've been telling you about this, and so maybe you struggle a little bit with your gases and adiabatic work and PV work and all that kind of stuff, and what happens to gases. Well, don't feel bad if you don't quite get it yet, because apparently even when you're a grown-up and have a degree in meteorology, you might not quite get it. So I told you about this. I was watching the news last fire season where we had these dry, hot Santa Ana winds, and they were fueling wildfires. So this guy was trying to explain that. So he said, dry air travels from inland California over the mountains and then down to the valleys. As the air drops down from the mountains, it's compressed. And we do know that is the case. There is a compression of that gas. And that compression happens adiabatically. So there's an adiabatic compression of the gas. And what does that do? That warms the gas. You do work on it, it warms it. So, but this guy, this guy says that adds friction to the air molecules, which heats the air. So we're here in Chem 1, and we can ask ourselves, our model for gases is that there's no interaction between the particles. The interactions are perfectly elastic. Of course, when we said real gases, that's not exactly true. There's some interaction energy. If there were real friction, what do you think would happen? So the particles are in, they have kinetic energy, but every time they hit each other, there's some friction, and friction robs them every time they hit each other of a little bit of their energy. So what's going to happen? There's a lot of friction in your gas, air molecule friction. Then the energy of the gas goes down, their kinetic energies drop because they keep hitting each other and losing some of their kinetic energy. Friction would cool off a sample of air and not increase the temperature of air. So a fixed air mass would cool off due to friction between the molecules. So don't feel bad that you don't have this yet. You have a couple of years till you get to doing weather reports. And by then, if you're a Berkeley grad, certainly not a Cal grad over there on the NBC Bay Area morning show. So let's do that. Let's do the question on the exam that we're going to redo has to do with this. A little bit, although I think it's an isothermal compression. So the one we're going to redo is this one. So which is true after pressure volume work is done isothermally on the system and it returns to equilibrium. So we're going to do that work, but it's going to be done isothermally. So what happens after that isothermal compression of the gas? Think about that and make your selection from the selections you saw last night. Talk to each other, help each other, think through this one. Remember, it turns to equilibrium. It was compressed. What?
People in the chat are not happy.
They're not happy about this?
No, they're not happy about the low midterm grade.
Yes, we're getting some friction in the chat stream because of the midterm average. Don't stress out. Low midterm averages happen, and we don't fail entire classes. This exam was a test of, like I said, you guys and us. So it was a probe, not a whip. We weren't trying to whip you. Maybe you thought the probe was like a COVID probe where they stick the cotton up into your brain. But we're all going to survive. So the stream is coming in. Mark all that apply. No, only one. Let's say only one applies. And also let's just even make it easier. As it returns to equilibrium. As it returns, or it gets to equilibrium. So what happens? You compress it, and then there's something that happens because it's an equilibrium system. One of those and you do know that I do that on the exam. I say mark all that apply a lot, and sometimes only one applies. I don't mean, that doesn't mean there's more than one answer. That means think about it and mark all that apply. Sometimes only one thing applies. What are you doing, Ryan? Okay. So let's, we have about 97. We'll give you 10 seconds here. If you haven't decided yet, choose one of them and we'll see what you're thinking. So stop the poll. I'll count down and we'll stop the poll. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. We'll stop the poll and then we'll see what you're thinking. Did we have an E? Oh yeah, there's an E there. Okay, good. So many of you chose the partial pressure of the dimer will be higher. I agree with those people. So nothing much changes. The volume goes down a little, and you need to relieve that pressure on the system. The temperature didn't change. So as you go towards equilibrium, as you reach equilibrium, the equilibrium will shift. And let's go back to my screen. The equilibrium will shift and you'll get an increase in the partial pressure of this and increase in the partial pressure here to get back to equilibrium. So that was the answer we were looking for there, D. So not many people got that one on the exam, but a lot of people have got it here and made that back up. That's great. So let's continue. There's one other thing I have to say about the exam, and it hurts me to say it. So we need you to be as forthright and academically honest, have high integrity when you take the exams. So we really don't want you surfing the internet and looking for answers or talking to other people. So there was this question where we asked you, what's the most accurate value for the standard enthalpy of formation for ethanol that can be calculated from the data in the table. So can you calculate delta H formation from the table? And you could do that because you had 2 enthalpies of combustion. So you could work those data backwards to get an enthalpy of formation for ethanol. And if you did that, you got 375. If you Googled the enthalpy of formation of ethanol, you would have got 277. Would have come up. So we're disappointed that so many people appear to have Googled that answer. So 2 things: don't do that, and it's probably not going to help you if you do. Essentially, we know that the internet's out there, and you're going to be tempted to do it. So by and large, we write questions that it's very hard to Google the answer for. That's one reason we can make them conceptual, and you can't find the answer for them. But let's get this under control. We can, as you know, B Courses tells us if you're switching tabs and going back and forth in and out of your browser. So some of that has to be done, but you have to look at an equation sheet, but browsing the internet certainly isn't allowed. I wish I didn't have to say that. So let's go on a little bit and talk about free energy and equilibrium. We were talking about that last time, and we already have this idea that these things kind of have to be related: the standard free energy difference and K. We have this idea because K tells us the position of the reaction. Does it favor products or favor reactants at equilibrium? And delta G tells us something about whether the reaction favors reactants or products. So if delta G is negative, standard state enthalpy of formation is negative, then that favors going towards products. If delta G is positive, standard enthalpy of formation is positive, it favors the reactant side. And favoring one side or the other influences the size of K. And in fact, it influences it in an interesting way. It tells us whether K is bigger than 1 or less than 1. So if K is bigger than 1, then the products are favored. And that seems to correspond to a fact where delta G is less than 0. So bigger than 1 and less than 0 seem to jive with each other. And the opposite is true as well. If delta G is greater than 0 and the reactants are favored, so if your reactants are very favored, then products are very small, and that's going to be a ratio of products to reactants less than 1. So small delta G's or small K's less than 1 indicate I don't go very far towards products, and that is also indicated by a positive sign on the standard state free energy. And when you think about this, you say, well, standard state free energy difference, that's everyone at 1 molar or 1 atmosphere of pressure, 1 molar concentration or 1 atmosphere of pressure. That's a very artificial condition. But it tells you everybody being equal, so everybody there in equal amounts, equal partial pressures, equal concentrations, if delta G is standard state free energy there under those artificial conditions goes towards products, then of course you started out, if every single one of these numbers is 1, then Q is 1. You put 1s in for everything, your equilibrium expression is 1. It goes from there towards products, then that ratio goes to less than 1. If it goes from there to reactants, then that ratio gets bigger than 1. So the standard state free energy has this idea. I start where everybody's equal, tell me where I'm going to go, and K tells me the same thing. So there's some kind of relationship between those, and we're not going to derive that relationship, but we're going to just notice what it is. So we say when delta G is greater than 0, that means K is less than 1, and we call that a non-spontaneous reaction. We've talked about that already. K less than 1, it lies towards the reactants as opposed to the products. Small, very small K is less than 1. K is greater than 1 goes towards products, and that's a free energy, standard state free energy, less than 0. If it's right in the middle, that's, like I said, the starting point. You put 1s in for everything, and the standard state free energy difference is, or when K is 1, I mean, this would be weird if the standard state system was equilibrium. If everybody 1 molar, everybody equilibrium. That would be it's a rare artificial situation. It's kind of our tipping point that we set up there. I don't think we ever expect it to happen. So this lends us to this reaction or this relationship. So this 0, greater than 0, less than 1, and less than 0, greater than 1. So something that switches from a fraction to bigger than 1 to a fraction less than 1 at 0 or at 1 is the natural log function. So if you take the natural log of a number that's a fraction, you get a negative number. So the natural log plot, if you plot the natural log, it looks like that, and that point is 1. If you go below that, below 1, you get negative numbers. You go above that, you get positive numbers. So that's the natural log function. So that is a function that switches a sign when you go from a whole number to a fraction. And that's what we want. So we want when K goes from a whole number to a fraction, we want the sign of delta G to change. And so without deriving it, we're going to just say, well, that fits the bill for what we want. So that's the reaction, the relationship we're going to use. The standard state free energy is indeed, as we suspected, related to the equilibrium constant by this factor of minus RT. Minus RT ln K gives me the relationship between free energy and the equilibrium constant. I can rearrange that, of course, taking the exponential of this quantity. So if I divide through by RT, take the exponential of both sides, that's the inverse function of the natural log. So that gives you an expression that looks like this. If I have K and I want to get delta G, if I have delta G and I want to get K, I can go back and forth with those two relationships. So that's interesting. That's a take-home thing. It jives with everything we've said so far, and it gives us quite a bit of power about predicting how things will go. So now we can go to a table and we can do look at free energies of products and reactants, and we have an idea where the equilibrium will lie. And if you want to produce something and you go to a table and you do your standard state free energy differences of your reactants and you find K very much less than 1 or delta G very positive, that's not worth doing that reaction. It's not going to make enough products for you. That doesn't mean, and now we also see delta G less than 0 does not mean I go to completion. That doesn't mean the reactants are completely favored or the products are completely favored. All that means is at equilibrium, there are more products than reactants. So spontaneous doesn't mean spontaneous doesn't have a time component to it. the word spontaneous seems like it has a time component to it. But as you know, time is not a thermodynamic variable. Spontaneous refers to the fact that when you get there, the products are favored. Can't tell you when I'm going to get there. So what's the standard state free energy change and K for this reaction? So this we've done many times. This is a phase change. The phase change reaction at 25 degrees C. What happens here? Think about that for a second and we'll take a vote. Okay. Here we go. We'll think about this one. Let's see what you are thinking. a lot of people are saying that the free energy difference in that state is bigger than 0, and K is greater than 1. So why are we saying that? I agree. Let me go back to us. So yeah, standard state is the boring state. So the standard state energy difference is what's the difference between this at 1 atmosphere and this pure liquid? What's the standard state free energy difference between those at 25 degrees C? So we know that gotta be a little careful here. We know that under these conditions that the reaction will go back back in this direction. This is too high a partial pressure at 25 degrees. We've seen the partial pressure many times. It's 0.003 atmospheres at the equilibrium partial pressure at 25 degrees C. So in this condition, in these set of conditions, the reactant side is strongly favored. So the reactant side is strongly favored. K is greater, or delta G 0 is greater than 0. That means at equilibrium, K will be less than 1, and we actually know that about K. The vapor pressure is K for that reaction. So that's one of those things where when you put that degree sign in there, that fixes the situation to everybody at 1 molar and 1 atmosphere. It's not an equilibrium situation, but it does tell us if you had 1 atmosphere there, then at 25 degrees, the liquid is the favored by the universe. Doesn't mean it all turns to liquid. In fact, 0.0303 atmospheres, there's too many zeros in there. It's 0.03, not 3 thousandths, it's 300ths of an atmosphere. There's still some gaseous water there, but the stable thermodynamic state is mostly favors liquid water. Oops, I can't do that. Yeah, I can't do it unless I... Come on. There's this thing where sometimes it doesn't really have to do with erasing everything. It just has to do with how you're holding the pen, usually. I will erase everything and see if that helps us. Sorry, guys. We know we can advance the slide without erasing everything, but it's not letting us do that right this second. There we go. Okay. So then we would ask the same thing. We could ask the same thing. What are delta G and K for the reaction in these set of conditions? So K is less than 1. Delta G standard is still greater than 0. Delta G standards doesn't apply to this state. It applies to the state at 1 atmosphere. So free energy and maybe I should say that one more time. The fact that I'm at equilibrium, the fact that I'm at equilibrium doesn't change the value of this. That's a constant, and this is a constant. So those two things are the same, whether I'm at equilibrium or not. The first time we were saying, well, what if you had 1 atmosphere? Well, of course, that side is favored. Now I'm at equilibrium, but that doesn't change the fact that the standard state free energy is still positive, because that's one set of conditions. It's not the equilibrium. It's not equilibrium. It tells you what the equilibrium constant is. It tells you the magnitude of the equilibrium constant, but it's not the equilibrium condition. This is going to do this So we looked at free energy and temperature before. We said that the standard state free energy difference, if I know the standard state enthalpy and the standard state entropy changes for a process, these two things, delta H and delta S, standard states are independent of temperature largely. They don't change very much. So that means if I plot delta G versus temperature, these two things we can treat as constant and plot it versus temperature, and we saw delta G versus T was a straight line. Now we know that delta G is minus RT ln K, so we can solve for ln K there, divide through by RT, minus RT. And if I divide through by minus RT, I get this situation, another straight line. So if I have a K, I take the natural log of it and plot that versus T, especially if I plot it versus 1 over T. So I have to do two things before I make my plot. I have to take the inverse of temperature and the natural log of a K, and then I can get a straight line plot. The slope will be minus the enthalpy over R, and the intercept will be the entropy over R. Why is that? You're going to say, why would I do that? I can already do the linear plot there. Let's look at a few conditions. We can look at our exothermic and endothermic interaction, and we understood this already. We said, well, when if you have an exothermic reaction, then we treat heat as a product. So if we treat heat as a product, so we're here in K, and we increase the temperature. Well, if heat is a product, we expect less product to be formed. We expect the equilibrium to shift towards the reactant side. That means a smaller K. So we expected K to decrease with temperature for exothermic reactions and to increase with temperature for endothermic reactions. And this strongly reinforces that. We did kind of this qualitative thing here where we said, well, heat's a product, heat's a reactant. This is quantitative now. You can, if you have a number for delta H, that does determine the slope of this line. So if delta H is negative, that's exothermic reaction, negative value here times that negative value gives you a positive slope and a negative slope for an endothermic reaction. So that's one of the reasons we go into this. Another very important reason we go into it is, how do you measure the entropy change? You know that in the lab you can do some experiments to get you an enthalpy change. You can do a calorimetric experiment, and you can often measure K because you have it's just difference in concentrations or pressures. So you can measure the concentrations or pressure using some kind of laboratory technique. So you can calculate at equilibrium, you can calculate all the pressures or all the temperatures, or all the pressures or all the concentrations, and calculate a K, as long as you know it's equilibrium. And you can do that at a bunch of different temperatures. If you do, and then you plot that, take the natural log of all your Ks and 1 over all your Ts and plot it, that is powerful because the intercept has this number in it, the entropy change of the reaction. And that's the hard one to measure in the laboratory. We haven't even thought of a way to do it yet. So there you can get what the standard entropy change is, a number for it. You don't just say, oh, entropy increases or entropy decreases. You get those numbers that you need to put in the table. So that's why we go through all that. And you can just go through the various combinations. I'll let you do this at home. You don't have to sit here and let me do it. Here are the many combinations of whether delta H and delta S are positive, both negative, and positive and negative combinations. So we've done it for delta G versus T. That was on the exam. You guys did very well on that. You understood that well. Here's the same analysis for the sign of delta H. Horrible. Yeah, Xfinity has just not been working. Is it completely stopped? Yeah, Xfinity has been just. Am I in real time-ish? Can you hear me? Yeah, I'm back in real time. Gonna take a pause there, guys. Apparently there was a hiccup, maybe on our end of the internet. Uh, internet has just been horrible for everyone. The uh, the 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 traffic, as you know, on the internet is always high, but now that everyone is using it for communication all the time, it's amazing that we have even the stability we do. So the internet traffic has just increased exponentially over the past 6 months because of this COVID and everybody working from home and everybody communicating from home. There are times during the day, and usually it happens around 10:30 when everybody starts going on, businesses are opening up, everybody's talking, that the internet speeds just drop. You can set your clock by it. Luckily, we meet early and we kind of get done before that really sets in. So I was just talking about the relationship between natural log k and 1 over t and the various combinations. Obviously, there's 4 ways, four related signs to the enthalpy and the entropy, and these are how the various plots look, and that gives us information about the value of delta S, sign and magnitude, and delta H. So here's a plot of natural log K versus 1 over T for this reaction, iodine solid going to iodine gas, which is this corresponding plot for carbon dioxide solid going to carbon dioxide gas. So think about this for a minute. There's 3 options that carbon dioxide plot. The lower one here, this is the CO2 plot. Looks like that. This lower one is the CO2 plot on that one. In case you can't differentiate the colors, CO2 is the yellow one in each case. The purple one is the iodine. How do they relate to each other? And this brings up a great point. When you're studying for the exam, I know you do the homework and you go through the questions that help you with the numbers. And in the first couple exams, there were a lot of questions with numbers, so you did better. This exam was more conceptual. That means you should be focusing on the chem quizzes. Make sure you understand the chem quizzes, because this sounds like a question you get on the exam. So think about that for a minute. We'll take a vote. Okay, let's see what you're thinking about this. We have to pick up the pace here. We're going kind of slow, so we'll see what Ryan has for us on the vote. The vote is, a lot of us think it's C, or half of us think it's C, and I agree. Oops, I want to do that and that. What do you know about these things? Well, I should have shown you that, would have helped, but you're going to compare these two reactions, and from what you know about entropy, you're going from a solid to a gas and from a solid to a gas, and you know that transition, the entropy is going to be pretty similar. It's just a bunch of solid particles going to a bunch of gas particles. Energetics doesn't have anything to do with that. It's all just how many states in the solid, how many microstates in the gas. Solids and gases, by and large, are very similar. So the going from one to the other, the change in entropy is very similar. So you'd expect the entropy changes to be pretty similar just from that argument. And you expect, of course, it's a huge increase in entropy both times because I go from a solid to a gas. And you'd expect them to be similar. So you'd expect an intercept that's the same, because the intercept of ln(k) versus 1 over t is the entropy. So you'd expect that to be about the same. The enthalpy, you would say, now you'd use your ideas about these two substances. You've seen this one, iodine solid to iodine gas. Iodine is a solid at room temperature. It makes the purple gas. We've seen that do that. Carbon dioxide is a gas at room temperature. You know that intuitively, I think. It's hard to get solid carbon dioxide. You know you have to go down to minus, what is it? It's minus, it's way below 0 Celsius. I think it's minus 50 Celsius or something. It's very, very cold. So this vaporizes much more easily than this. If this vaporizes much more easily, its enthalpy of vaporization is lower. That means a less negative slope, not a more negative slope. Excellent. So we'll just go through then. We've talked about the standard state free energy difference, but you can measure the difference between products and reactants all the time. So if you look at the difference between the products and reactants at any point, any value of Q, for instance, then you could say, well, if the free energy of the products or the reactants is too high relative to the free energy of the products, then it's going to make more products. And if the free energy of the products is too high, it's going to make more reactants. You want the free energies of the products and the reactants to be the same. They're never that case really under standard conditions. That's where everything is equal. Free energy depends on all the situation, everything that's going on in the system. It'd be incredibly rare that everybody at 1 molar or 1 atmosphere would be equal free energies. And we know that. Standard state free energy differences are almost never 0. You can look at the tables. But during the reaction, they shift. So you could say, well, I'm at this weird situation where everybody is 1 atmosphere. I'm at the standard state, but the free energies are quite different. The concentrations are all the same. Free energies are quite different. So as it moves, you can plot the free energy at every point, an instantaneous free energy. And it makes sense that that would relate to Q, which is the non-equilibrium description of the reaction. And it absolutely does. So we know when Q is less than K, then Q is too small. I need to make products. I need to go towards the product side. And that corresponds to the free energy difference at that moment between the products and reactants is less than 0. So I need to go towards products. If that instantaneous free energy is 0, now this is a case where this is a reaction free energy, can be 0. We said It'd be odd if the standard state free energy differences were 0, but this can totally be 0. In fact, it always is when you get to equilibrium. That's the condition for equilibrium. The free energy differences between the products and reactants instantaneously are 0. The universe is indifferent to whether I go and make a product or I go and make a reactant. So it just happens interchangeably. You'll have products making reactants, you'll have reactants making products. There's that dynamic equilibrium. And the reason it can be dynamic is the universe doesn't care. You may be either one. And of course, the opposite case, if delta G is greater than 0, that means Q is greater than K, and I have to go back towards reactants. So we can summarize that like this. The instantaneous free energy change is related to that standard state free energy change. You adjust it by Q. So if you have this from a table and you know Q, you can figure out what the instantaneous reaction free energy is. Remember, that one's a constant. This one varies. This one's a constant at a constant temperature. If we put that temperature and K in there, so if we put K there, we know that is delta G. It's minus delta G. So when you get to K, then you have a plus delta G there and a minus delta G there. And of course, you're at equilibrium and the instantaneous delta G is 0. And see, that's interesting because right there, I did a swipe. Even though there was an annotation, it said fine. And in this case, the annotation's in the way because the annotation and the animation are the same. Okay, I'll talk through this for you then. So what's the instantaneous now? Delta G. Oh, Lord have mercy. Why is this thing giving us so much trouble today? We just have no idea why it is doing this. So now I want to know the instantaneous delta G and K for the equilibrium at 25 degrees C. Well, it's kind of a stupid question because if it's at equilibrium at 25 degrees C, then that is 0. That's the definition of equilibrium. The instantaneous free energy is 0. So it kind of has to be this one. What about K? Well, K didn't change just because we're looking at the instantaneous free energy. K is still K. That's just a constant with the temperature. So K has been the same. Every single one of these chem quizzes with water, K has been the same number. This case, we're just saying, well, what is delta G without the 0, without the free energy, out the standard state? And of course, if we're at equilibrium, it's 0. That is the whole idea. I really don't know what's going on today, but I'm going to stop doing this PowerPoint annotation because it's obviously driving us crazy. So here we did this one already last time. We said, what if I perturb the equilibrium? What if I add reactants? And if I add reactants, then it's products over reactants. Q is less than K, and the equilibrium will shift. So let's just work through one. So delta G for the following reaction. So we have N2 and H2 going to NH3, all in the gas phase. This is a famous reaction for fixing nitrogen and hydrogen to make a compound that's reactive. This is a reactive compound of nitrogen. This is unreactive. So if you can make this, you can do lots of chemical things. This is responsible for that horrible explosion last night in overseas in where was it? Beirut. One of the port in the Middle East exploded because they were storing ammonium nitrate, and it's unstable. And of course, it's what you make dynamite out of. The whole thing blew up. So what if you have those values? So these are the actual conditions. These are the pressures. They're partial pressures in bar, same as atmosphere, about the same number. So I can write down Q. So I can write the expression for Q. I can plug those numbers in. 21 atmospheres, 4.2 atmospheres, 1.8 atmospheres. And I can calculate a number. It's 18. So that means this is not at equilibrium because K is 41. So this is not an equilibrium situation, and Q is less than K. So if Q is less than K, products over reactants, I need to make K bigger. I need to make more products. The reaction will shift towards making products. What about the free energy? Well, I can get the instant free energy because I can get this number. Oh, I said I wasn't going to write on the board with this thing anymore. I'll write on the board with that thing. I know that's okay. This delta G, what is it instantaneously? I know it's not at equilibrium, so the reaction wants to go one way or the other. I know the sign because it's going to go that way. So this number better be negative. It's going to favor it's going to go towards products. But if I know this, and do I know this? Not going to give you that on the exam. Do I know standard state delta G for this reaction? Yeah. It's minus RT ln K. K is a constant. So I know delta G. If I know K, I know the standard state free energy difference. So I don't have to give you that number to do this question. You should know I can put delta G in there. And of course, I can put that Q because I just calculated it there. So I can do that. And I can write down, I get my delta G from minus RT ln Q. There's R in joules. There's the temperature 400 Kelvin and natural log of 41, which was K. And I get minus 12 kilojoules per mole of reaction. If I form 2 moles, I have to multiply that by 2. So what is delta G? Well, now I can take it. There is the standard state free energy difference for the reaction as written. I subtract away the value of Q, and I get that the instantaneous free energy difference is indeed negative. Oops, want to go through that again? Oh, what do I do? Oh, yeah, the reaction proceeds towards products. That's what we're going to say. Not sure what I was doing here. I think I went, I go to a different temperature? Not sure what I was doing here. I think I was messing around. Okay, so let's continue our discussion of equilibrium. So this time we're going to go to heterogeneous equilibrium. That just means phases are different. So we've been saying, well, let's try to keep everybody in the gas phase or everybody in the liquid phase, everybody aqueous, so that we can understand the equilibria. But you can have gases dissolve in liquid. So if you have a gas dissolve in a liquid, that means you could have a partial pressure of carbon dioxide over a solution, and some of the carbon dioxide will dissolve in the water. And that's that is mediated by an equilibrium constant. There's an equilibrium constant for this reaction. And we can write that down. We can write down the expression for the equilibrium. And we can give it, call those things a constant. But now we're saying it's the concentration products over reactants in a partial pressure. That constant, then, we tabulate, and we tabulate it like this, and we give this a special name. I'm not sure why. Henry's law constant. Basically, that's an equilibrium constant, and we can get the concentration of what's dissolved if we say multiply the partial pressure above the solution by the equilibrium constant, we get what's dissolved. If we know the concentration of what's dissolved and the K, we can get the partial pressure. So here are some various values of how various gases dissolve. So helium is not very soluble. If you have 1 molar or 1 atmosphere of helium, K is 0.04, so you'd have 0.04 or 0.4 molar helium in the solution. Carbon dioxide, quite a bit bigger, K. So this, if you have a concentration of X molar, this is quite a big number relative. So you'd have this partial pressure doesn't have to be as high to get that concentration. This says low partial pressure will give me a high concentration if K is big. So low partial pressure. So if I'm trying to get it to dissolve, I'm trying to add increased partial pressure to get it to dissolve, then a high K helps me do that. The gas is more soluble. So we can see Lonnie demonstrate that. So let's look at that. Hopefully the web is will go quickly enough for us to see it. We're in the demo lab where Lonnie's prepared to demonstrate the solubility. So what Lonnie's going to demonstrate here, he's going to take the ammonia gas here, and ammonia gas is very soluble in water. So this has ammonia gas. Here's some liquid down here, and there's a tube connecting the two. He's going to squirt a little bit of water into that tube. When he squirts a little water in there, the ammonia really starts dissolving. Very high equilibrium constant favors the dissolved state. So as that ammonia gas starts dissolving, what happens? Well, we're removing gas from that flask. If you're removing gas from that flask and it's dissolving in the liquid, the pressure inside that flask is going down. So if the pressure inside that flask is going down, we have pressure inside that flask is going down, the atmosphere is still there. So the pressure is going down, the air pressure here forces the liquid up through this tube and into the flask up above. So low pressure here, high pressure here, and that's forced up the tube. And you might have said before you got to this class that you're starting to create a vacuum here, so it sucks the liquid up. Vacuums do not suck. That's not what's happening. High pressure pushes the ammonia up there. And that's dramatic. That means the free energy difference between the dissolved, this is actually, you can see the free energy difference between the products and reactants, because that reaction going lifted, you know how heavy water is. This is probably a kilogram of water already. So the free energy of that reaction lifted, the release of energy was sufficient to lift that water up into that tube there. So free energy, in fact, free energy is, another definition, the energy available to do work in a chemical reaction. Free energy difference says, how much work could I get out of that if I did that reaction? Well, there you go. I can get some work out of that. So notice N2. These are dependent on pressure, as you know. So if you have a higher partial pressure, you get a higher concentration of the gas in your system. If anybody's out there a scuba diver, you may know all about this. When you dive, you breathe in air, compressed air. Compressed air has nitrogen gas. It's mostly nitrogen gas, just a little oxygen in it. So if you dive deeply and there's a high ambient pressure of the nitrogen, then at high pressure, the nitrogen is more soluble in your blood. So you get nitrogen dissolving in your blood as well as the oxygen. And that would be fine, except that it's hard to get the nitrogen back out of your blood. Well, it's not hard to get it out. It's hard to get out of your body after it comes out of the blood. So if you dive deeply and you stay down there and you're breathing this nitrogen-rich gas the whole time, the nitrogen is dissolving in your blood at a much higher rate than it would if you were at the surface. And then you ascend, you rapidly drop the ambient pressure, partial pressure of nitrogen. So that nitrogen wants to come out, bubble out of your blood. And it does. And it's extremely painful. The bubbles collect at your joints, and you get something called the bends. It's a diving thing, and it's called the bends because it's so painful. Every joint hurts, and they're bent over in pain. That was those. So when you dive, there's tables that say you can stay down this long at that depth and come up safely. If you stay longer at that depth for that time, if you come up, the nitrogen, the amount of nitrogen in your blood is too high, and it will come out of your blood faster than your body can get rid of it by breathing or by expiration. So those tables were empirically formed. They had these poor Navy divers back in the day, and they would send the Navy divers back, deep dives, and they realized, oh my God, there's this bends thing. We can't leave them down there that long. And they realized it was a function of how long they stayed down. So they just started taking notes. Oh, dude, you were down there how long? Oh man, that looks like it hurts. So they would say, don't stay down that long. And they just did that for a long time. And they come up with those tables of how long you can stay down and not get the bends. Dude. Sorry. We're gonna make a note of that. We're not gonna let anybody do that again. I'll walk you through this one. A solution has equal concentrations of nitrogen and helium. Equal concentrations in the system. I didn't draw the little picture, I guess, but you have nitrogen molecules and helium molecules dissolved in here. They'll be in equilibrium with the pressures above it. So, which is true of the pressures above it? Well, it depends on how soluble they are. Helium and nitrogen, and we saw the relative solubilities, the relative Ks. Nitrogen is a little more soluble than helium. So to get helium at that concentration, you'd need a higher pressure than you would of nitrogen because K is smaller for helium than nitrogen. So if that's the case, that there is more helium in the solution and it's at equilibrium, the partial pressure of helium must be higher, same concentration, different K. So to get, you'll have to have a higher P to get that those concentrations. So the concentrations are equal, but the K is smaller. So HE must be higher to get that system to agree. Essentially, helium, nitrogen is more soluble, so you need a higher partial pressure of helium to get the same concentration in the liquid. So we've all seen this. On a warm day, a carbonated soda expands. What can we conclude about the dissolution of carbon dioxide? Is that exothermic, endothermic, or does that dissolution proceed without, is it isothermal? Does it proceed without changing? So we can talk through that. Actually, we have, we'll talk through it. Carbonated beverage expands when it's warmed. So if it's expanding when it gets warmed, that was the same thing as you coming up from the deep dive. The gas was coming out of solution. So that means the gas is coming out of solution as it gets warmed. So how much animation do I have for this? So you know that this is the equilibrium, and there's an equilibrium constant at one temperature. But I'm going to go to a different temperature. And a different temperature is higher. And I notice that I get a greater pressure of carbon dioxide at that higher temperature. So if I'm favoring this, I'm favoring the gas side at a higher temperature, which is probably true. Well, it probably means heat is a reactant, our product. So it's probably an exothermic reaction. So we know the partial pressure goes up. K got smaller with increasing temperature. K gets smaller with increasing temperature. That's characteristic of an exothermic reaction. So there you go again. This question looks a lot like an exam question that we had this time. You didn't have, there were no numbers. You had to know something about K and how it influences T, or how temperature influences K, but we weren't talking exactly about that in the question. So if there were a lot of questions about carbon dioxide gas going to carbon dioxide aqueous, this might have been one of them. And you determining whether it's exothermic or endothermic is certainly a legitimate thing for us to ask you in that situation.
There's a question.
Yes, question.
How do you know to put gaseous CO2 on the left side?
Because I said, so a good question. How did I know to put this as the reactant and that's the product? And that's just how it was worded. What do you conclude about the dissolution of carbon dioxide? So the gas dissolving in the liquid. Good question. So you had to know what that word dissolution means, but I think you know dissolving means going into solution. So that's the direction of the reaction. Good question. So there are soluble and insoluble compounds. When you talk about taking a solid, this is another heterogeneous equilibrium, a solid equilibrium with aqueous ions. Some solids are very soluble. So if you looked at this equilibrium, you wouldn't put in the pure solid. So the equilibrium expression would just be the product of the ion concentrations, because overreactance is one. The solids and pure liquids appear as unity in the equilibrium expressions. So in fact, we call these equilibrium, and Ryan told you about that when we first started this, we call these solubility product equilibrium. Doesn't mean, KSP doesn't mean it's not K anymore, it's just a label. So everything you know about K still applies. Just because I put the SP down there, it's just telling us it's a solubility product, because that's what it is. It's a product of two concentrations. And that's an equilibrium. So if K is small, then the product of these two concentrations is always small. If K is huge, then the concentration of these can be very large. So you can see K determines the solubility. If you have a big K, it's very soluble. Your concentrations are allowed to get large. The product of the concentrations is always fixed. It's not one concentration is big or the other concentration is big. Their product is fixed. That means if you had a lot of this, this would have to be small. In this case, they're both coming from the same source. So they'd be equal and small. So if K is small, in fact, this is a not very soluble thing. K is 10 to the minus 10. Lord have mercy. So almost none of this dissolves. The product of these concentrations is 10 to the minus 10 all the time. That means one set of conditions, the equilibrium set of conditions is this one is 10 to the minus 5 molar, and that's 10 to the minus 5 molar. That's crazy small. So almost none of it dissolves. 10 to the minus 5 molar, 10 to the minus 5 moles per liter. Virtually none of it dissolves. And that product stays fixed. So if I said, oh, well, there we just did the calculation. If some of it dissolved, if a little bit X, if a little bit X moles dissolves and X moles of that dissolves at equilibrium, then the equilibrium constant, the equilibrium expression would say, well, X squared, it's the concentration of that times the concentration of that, at equilibrium has to be the equilibrium constant. And that's how I'd get 10 to the minus 5 molar.
Some questions.
Yes.
What does EQU after KT mean?
The question is, what does EQU over KT? Oh, equilibrium, I guess. That doesn't have to be there. It was this. The question is, why is this EQU here? And it's actually distracting. It's just the equilibrium constant. At equilibrium, Q is K.
Why is 10 to the negative
The value of the question is, the value of K is 10 to the minus 10, 1.1 times 10 to the minus 10. The value of the concentrations, so K is always the product of the two concentrations. So if the concentrations are equal, then each one has to be 10 to the minus 5 to get to those products. 10 to the minus 5 times 10 to the minus 5 is 10 to the minus 10. Yes?
What if you have two salts that share one of the two ions?
The question is, what if you have salts that share the ions? And of course, that's actually the next thing we'll talk about. So we'll just start talking about it. Of course, you could, if these ions came from some other source, this product still has to be all equilibria. And if you take nothing else home from Chem 1A, take home the fact that all equilibria that are relevant in the solution must all be satisfied at the same time. So you can't have another salt or another thing providing SO4 sulfate ions without that equilibrium and this one being solved. So if SO4 is coming from something else and that makes this go to a higher concentration, 10 to the minus 4th, then this concentration has to go down. So there's still the product of them is still K. So simultaneous equilibrium, multiple equilibrium, we talked about that before, how we can multiply Ks and arrange equilibrium constants by looking at various reactions. Every equilibrium constant, every system has to be at equilibrium at the same time if you're at equilibrium. So we'll just go through this then. Which of the following is required to dissolve the least amount of barium sulfate in solution? So you have a little speck of barium sulfate solid in your solution. You want it to dissolve. Should you add 0.1 molar H2SO4? That dissolves to make sulfate ions, very high K. This one, very high K for dissolving. So you'll get lots of barium and lots of chloride ions. Or pure water. What is the best way to make that dissolve? Think about that for a minute and we'll talk about it. Okay, there was a question that came in. Finish up your voting on this. The question was, do I have to know about solubility rules? That is, what makes a compound more soluble? What's the general trends in solubility? No. For an exam, if you want to look at that, it's very interesting, but it's never going to appear on an exam in this class, which I think means no one will ever look at it. I don't think the solubility rules help you moving forward in life. If you want to look up how soluble something is, look it up. Back in the olden days, you didn't have the internet and you didn't have tables and you didn't have all this stuff. So if you wanted to know how if sodium sulfate was more soluble than sodium hypersulfate, some solubility rules might help you. Yeah, nobody does that anymore. Ryan told me it's still on the AP chemistry exam. So as you can see, the AP chemistry test is in the Stone Ages. So let's talk about this. So now you're saying, this is the equilibrium I want to influence. That is, I would like more of this to dissolve. I would like to push the equilibrium in that direction. I can't do that by adding more barium. I can't do that by adding more solid. Doesn't appear in the equilibrium expression anyway. Doesn't do me any good. Do either of these things help me? Well, if I add those things, I told you barium chloride is quite soluble. So adding barium chloride increases the concentration of barium ions. That would push this reaction back towards the solid, make it less soluble. Same thing with the SO4 ions appearing in solution. They'd make it go back in the other direction. What I want to do is make these two numbers smaller, reduce those two concentrations. How do you reduce their concentrations? Well, if you add water, if this goes from 1 liter to 2 liters, then the concentrations are cut in half. I still need to be K. I'm not K anymore. So I would shift and I would dissolve a little more solid, get back to concentrations that are the same. In this case, the same, because it was only coming from here. Get back to where it satisfies the equilibrium expression. Okay, I think what's today? Wednesday? I think we're done, and I think we're almost done with this whole section, so that's good. We're more or less on schedule, I think. You can see the syllabus online has been modified to take into account we took yesterday off, so you'll see that. It means in general, we're just going to cover a little less material than we were originally going to cover, much less, because we had some extra days at the end anyway. And Chem 1, it varies from semester to semester, whether the instructor's discretion. We can talk about kinetics, or we can talk about electrochemistry, or we can talk about one topic a little more than another. So we'll decide what we're going to do. We're going to start acid and base discussion next, and we'll see where that takes us. Okay, guys, we'll see you tomorrow. Please, I hope you're relaxing over the exam. We're not going to fail everybody in the class. Don't have a cow. We're going to make sure that there's the appropriate distribution of A's and B's and C's based on your effort and based on a straight scale that we probably will have to adjust a little bit. Who knows? Maybe you'll just crush the final and do great. All right, that's it. See you tomorrow.